Hello, Integrated Math 1. Welcome to lesson 3.1.2a. We've been playing with our exponential functions, and now we're going to start comparing them a little bit. So we've got the format down. Now let's see when we start comparing them across the board to one another. So we have a few learning goals, obviously. First of all, we're going to write the exponential equations. We're going to write exponential equations to represent situations, tables, graphs. Remember to write it. All you need is a y-intercept and a common ratio, and you can write the exponential function. So we'll be looking at our situations, tables, graphs, and sorting that out. We're going to solve simple exponential equations using common basis. We're going to actually save that a little bit more for next time, but that is coming up. And we'll compare exponential equations in different representations, right? Tables, graphs, situations, equations, and compare them across the board. So you have used geometric sequences to define exponential functions. How can you use what you know to compare exponential functions represented as a situation, equation, table, or graph? So just a brief reminder before we go any further, we've already learned this, but just to remind ourselves, remember that with an exponential equation, it comes in the form f of x equals a times b to the x power. And so all you need is that y-intercept. Remember, for a y-intercept, you're looking for where x equals 0. Ooh, sorry, my pen went funky there. Try that again. Fix it. Better. So we're looking for where x equals 0, or maybe we're looking for where it starts, right? How much we have to begin with. Something along those lines is usually what we're looking for in a y-intercept. And of course, this is our constant ratio, right? Are we multiplying by 3? Are we multiplying by a half? What's happening every time? And if we have those two pieces, we can write the equation. So let's start off with the amazing Aloysius. He's practicing one of his tricks, and as part of the trick, he cuts a rope into many pieces and then magically puts the pieces of rope back together. He begins the trick with a 10-foot rope and then cuts it in half. He takes one of the halves and then cuts that piece in half. He keeps cutting the pieces in half until he's left with a piece so small he can't cut it anymore. So what I would like you to do is to complete the table to show the length of rope after each of Aloysius's cuts. I'll get there. So write each length as a whole number. You could write as a mixed number or fraction. But yeah, give me a whole number, mixed number, fraction. I am going to ask no decimals at this point. I'm sorry. I'm going to ask for no decimals. And then once you've filled out your table, go ahead and graph it over here. Use the points X and Y to graph it on the little graph on page 25. So go ahead, hit pause to work this out, and then hit play when you're ready to check your work. Are you ready? So we started off with 10 feet of rope. So there's been no cuts made yet. We have 10 feet of rope. Of course, after one cut, we cut that in half. So it's 5. Cut it again, and you get 5 halves as I plunge into darkness. If you don't like writing it that way, you're welcome to write it as 2.5. If that makes you feel better, that's totally fine. If we cut that in half, oh my goodness, if we cut that in half, we get like 5/4, right? Which is like 1.25. Fair enough. If we cut it in half again, oh my gosh, we cut it in half again, that's what, like 5/8? Oh my goodness. Oh, and see, that's not even here. I can't even like simplify that anymore. It's just 5/8 now, isn't it? Oh. 5/8. If I cut it in half again, I end up with 5/16. We're getting pretty small here. So if I go ahead and graph this, if I'm like, okay, that's my X, that's my Y, so 0, 10. So 0, and then all the way up to 10. There's my first point before we even cut anything. After one cut, I have 5 feet of rope. So one cut, 5 feet of rope. After 2 cuts, I have 2.5 feet of rope. So second cut, here's 2, and we'll go halfway up to 3. There it goes. Three cuts. I'm skipping ahead. 3 cuts gives me 1¼ feet of rope. So 3 cuts, we go 1, and then a quarter is a bit more than that. 4 cuts gives me 5/8. I don't know exactly where 5/8 is, but I know it's more than a little over a half, right? 4/8 would be a half, so I'm a little over that. So 1, 2, 3, 4 cuts and half. And we'll just go like a hair above that and be like, there's 5/8. 5 cuts gives us 5/16. That's less than a half. It's small. We're just going to put it like down here. It's hard to know exactly where it is, but we get the idea. We get the idea. It's not perfect, but we get the idea. All right, so we have our table. We have our graph. Hazan, happy day. Let's take it to the next level then. Wait a minute. There it is. Can you use this? Use your table, use your graph, use whatever you've got. Can you please write the function? And instead of f of x, we're going to call it L of C to represent the length of the rope, L, as a function of the cut number C. So go ahead, write your function, hit pause to write it out, hit play when you're ready to check your work. So f of x equals a times b to the x power, right? That's our deal. That's our thing. And we said, this is our y-intercept. This is my common ratio. Well, my y-intercept is how much rope we had at 0 cuts, which was 10 feet of rope. So my y-intercept is 10. B is our common ratio. And we said the pattern was we were cutting in half, right? Cut in half, cut in half, cut in half, cut in half. So that sounds to me then that my constant ratio is 1/2. And now I can write the function. Instead of f of x, we're going to call it, and I'll use my pen here. Instead of f of x, we'll call it L of C. All right. And instead of a, that's our y-intercept, I'm going to put a 10 there, times my b value is my constant ratio, which is 1/2. And it's going to be raised to the x power. Yay, there's my function. Actually, I'm going to erase this. I'll show you the typed one because it's prettier. It's all typed up. So nice. And there's our function. The length of rope depends on how many cuts we've made. And so this is where, I made a mistake. That shouldn't be an X. That should be a C, shouldn't it? Oh my goodness, Miss Scott. What is up with this today? So that should be a C for the number of cuts. My apologies. I put 1/2 to the X power. If I have a C in here, it should be 1/2 to the C power. All right. You have your function. Can you please use it? And that means you're going to want a calculator nearby. Can you please use it to determine the length of the rope after the 7th cut? Go ahead, hit pause to work this out, hit play when you're ready to check your work. So I'm going to use my function, which we said was L of C equals 10 times 1/2 to the C power. All right, only we said it's going to be the 7th cut, so I need to plug in a 7. So 10 times 1/2 to the 7th power. Woo. All right, this is why I want a calculator. So this is 10. 1 to the 7th power is 1. I need my calculator. I need to do a quick little bit on my calculator. I don't know what 2 to the 7th power is off the top of my head. I don't know that. 2 to the 7th power is 128. I guess I should have known that one. Oh, well. So 2 to the 7th power is 128. So this means I have 10 over 128. I can simplify that, right? Because I can divide both of those by 2, right? Divide by 2, divide by 2. 10 divided by 2 is 5. 128 divided by 2 is 64. So I have 5/64 of a foot of rope left. That's not a very big piece. But that's where we're at after 7 cuts of the rope. Okay. So now that you got the feel for this down, now that you got the idea of like making the function, in this case, we made the table, we made the graph, and then we wrote the function. On page 26, question number 4, I have 4 of these for you. You got a couple tables, you got a graph. I would like you for each one, table A, table B, table C, graph D, I would like you to write the exponential function for each one. Go ahead and hit pause to work these out. Hit play when you're ready to check your work. All right, so we know it's f of x equals ax plus b. I know a is the y-intercept. Here's my 0, so my y-intercept is 4. B is the common ratio. Well, I went from 4 to 2 to 1 to a half. Oh, I'm cutting it in half, aren't I? Right? Do you see that? If you don't, maybe you saw it as divide by 2, divide by 2, divide by 2. And that's fine. But that means that your common ratio then is going to be, you're going to multiply by a half. Instead of saying divide 2, we want to multiply. So we'll say that we're multiplying by 1/2. So my constant ratio is 1/2. And now I can write my function 4 times 1/2 to the x power. Please remember, with it being a fraction, that you've got to have parentheses around that fraction, that it's 1/2 to the x power. You need parentheses around it so that's the whole 1/2 is going with it. How'd you do on B? This one looks scarier, but it wasn't that bad. I'm still doing f of x equals ax plus b. For my y-intercept, I'm looking for where x equals 0. That's where it is. Oh. So my y-intercept is -8. Oh. And my pattern, well, I went from 1/2 to 2, -1/2 to -2 to -8 to -32. I had a little hard time here, but I realized from here to here, we're multiplying by 4. And that happened again here to here. And I realized that if I was careful, 1/2 times 4 would also give me 2. So -1/2 times 4 is, in fact, -2. So it does look like then that my constant ratio is 4. Sweet. I'm going to write my function. F of x equals -x times 4 to the x power. Yay. How'd you do on C? So for C, I started off at f of x equals a times x times b to the x power. My y-intercept is where x equals 0. So here's my y-intercept. It's 1. Since that's where x equals 0, my y-intercept is 1. My pattern, I went from 1 to 4 to 16. Oh, we're multiplying by 4 again. This one was actually nicer than B, wasn't it? Oh my gosh. Okay. That was nicer than B. I'll take it. So that means my constant ratio is 4. So that means I can write f of x equals 1 times 4 to the x power. Now I'm going to point out, because my y-intercept is 1, you actually could get away with writing this as f of x equals 4 to the x power, because 1 times anything is the anything, right? And so if you wrote it this way, that's fine. If you wrote it this way, that's okay too. Both ways of writing it are correct. I kind of like this because it makes my y-intercept a little more visual, right? Ooh, last but not least, the graph. How did you do with the graph? I'm curious how you did with the graph. So again, f of x equals a times b to the x power. So this means I've got my y-intercept right here. And it looks like my y-intercept is at, was it -1, -2, -3? Oh yeah, looks like my y-intercept is at -1. So that's convenient. Now, did you have a hard time finding the constant ratio? So you know what I did is I actually made a little mini table. I made a mini table and I wrote down the points, right? X and Y. And I wrote down the points and I was like, okay, this is at 0, -1. And the next point was at 1, -3. And the next point was at 2, -9. Do you see the pattern now? Let's see the pattern. So I found it helpful just to write down the points in a table. And then I was like, oh, look, it's times 3 times 3. So my constant ratio is 3. So that means my function is f of x equals -1 times 3 to the x power. Yay. As always, guys, I hope you found this helpful. I hope you found this useful. If you got questions, concerns, come talk to me. And I'll see you guys soon. Bye.